I am really delighted this morning to introduce our speaker and welcome Professor David Seidman of Northwestern University to the Wilson Forum. David is the Walter Murphy Professor Emeritus of Material Science and Engineering, and he's the founding director of Northwestern's Center for Atomic Probe Tomography. Now, we have a little bit of a disconnect in a sense here today. David could not open the the PowerPoint presentation that he intended to present this morning. So instead, he's going to present a slightly different one on the same topic, but not exactly what he intended. So David, I'll leave it to you to make the adjustments as you go forward. Welcome to the Wilson Forum, and thanks for joining us this morning. The floor is yours, David.
Okay, thank you very much. The abstract is 50% correct. The 50% that's correct is to explain to you first what is an atom probe tomograph and why it's useful to look at things on an atomic scale. The second half, I had picked two examples that I thought may be of interest. One is about a meteorite, Allende meteorite, which is weighed about 2 tons when it hit the Earth. So it's like a big car. And the other topic I was going to talk to you about, and it contains nanodiamonds. And nanodiamonds are useful, actually, it turns out. And there are 2 places in the world that I'm aware of where they're building what they call nanodiamond foundries, but they grow them by layer rather than taking them from a meteorite. And the other examples I was going to talk to you about involve looking at interfaces in silicon nanowires. But I'm going to talk to you today about the examples will be different, but they're still useful in a practical sense. So I like to look at problems that have at materials, I should say, that have that are technologically important, but I like to try and get science out of those problems. So it's an admixture of my approach. So let me begin the talk. So first, I'm going to explain to you 3D atom probe tomography, and then I'm going to explain to you what is a local electrode atom probe, a so-called LEAP. And the examples in this particular talk are these 4 examples here of magnetic tunnel junctions. I'm not going to talk about that. I think I'm going to talk to you about formation of nickel silicide thin films because they're relevant to integrated circuits, particularly because they involve silicon and then also important metals for integrated circuits, nickel and palladium. And then the last topic here is phase separation in nickel, aluminum, chromium model superalloys. And superalloys are important because one makes turbine blades out of them for jet engines and also for land-based natural gas-fired electrical generators that produce electricity. So there you see there's something that's scientific and something that's technologically important. So let me get started with the atom probe tomograph. Okay, so here is an image. Here is an image of a nanotip. It has a 110 orientation, which means it has 2-fold symmetry. And you can look at this and you see a series of concentric circles. And those concentric circles are a result of a sharply pointed tip. By sharply pointed, I mean less than 500 angstroms. And those are atomic planes. And if you look at some of the planes here, you can see individual atoms. I don't know if my cursor works for you, but down here there is a plane and you see atoms on one plane here, and then there's a plane below it. And one of the capabilities of the atom probe is that you can dissect the tip one atom at a time, essentially, but at a very high rate, and then reconstruct it in 3 dimensions. Can you?
For reference, we can see your pointer perfectly, so that's working.
Okay, so look at this plane over here. This is a plane, and how many atoms are there? There's 2 and 3, 5. There are 7 individual atoms, and by pulsing it with either electrical pulses or with a laser pulse, you can dissect that atomic plane. And at the same time, you're dissecting other atomic planes. So you collect a lot of information in 3D, and it's possible with algorithms then to reconstruct that information in 3D and then look at the tip and all its atoms on a high resolution screen. Okay, so here's how it works. Here is a tip, and you can see atomic planes here, and the planes alternate between blue atoms and red atoms, and then you see some green atoms. So you can consider those green atoms to be impurity atoms. And now you dissect the tip. I'm going to dissect it, and you see atoms fly off the tip, and they're collected on a screen. And on the right-hand side here, you see there's a curvature. That curvature is artificial. The planes are flat. And the reason that it's artificial is that the tip to screen distance, and this screen over here is really a detector of atoms. And it's small. It's between 80 and 120 millimeters. And that introduces curvature because an atom evaporating from this point over here has this flight path, and an atom evaporating over here has a different flight path. And that introduces curvature. And then what you do is you flatten it out, and you see in the lower right-hand corner here, you see this is a reconstruction of that tip.
Yep.
Okay, now here is it happening. This tip over here contains these clusters of orange atoms, and there is a cone here through which they pass, and that's called a local. And then they hit a detector over here, and the detector does two things for you. It determines the time of flight of the atoms, and from the times of flight of the atoms, you can determine the mass to charge state ratio. And you notice there's a grid here. There is a grid here, and that tells you where in space those atoms are located. And with that information, you can do a complete 3D reconstruction. Okay, in the lower right-hand corner here, you see the instrument, and there's a lot of ultra-high vacuum equipment here that goes into it. The tip is very tiny. Someone once asked me, "You have such a tiny tip. How come you need so much equipment?" Well, because you have to do a lot of processing. Now, it's a commercial instrument, and at that time, the company was called Imago, and it was a startup company in Madison, Wisconsin, by a former professor, Thomas Kelly, who was a friend of mine, actually, before he became an entrepreneur. And now it was bought by a company called Amatec, which is a publicly traded company worth about $47 billion. And this part of it is called CAMECA. Okay, so what can it do? It can analyze volumes, and it can analyze a volume something like 10 to the 6 cubic nanometers. Wow. And the vacuum is ultra high. It's 10 to the minus 10 torr. Actually, now we can even do much better. We can get to about 2 times 10 to the minus 11 torr, and that's important for getting very clean mass spectra. The tip is at a low temperature, 20 degrees to 100 degrees Kelvin, and And the reason for that is this is the, there's a couple of reasons. Let me just tell you at this point, it's between 20 to 100 degrees Kelvin, and I'll tell you a little bit why that's important. You can pulse with voltage pulses at a repetition rate of 250 kilohertz, and you can pulse with a picosecond laser at about 500 kilohertz. And over here, I say it's a green laser. We now have an ultra high vacuum. I'm sorry. We now have a light that's a laser light that's 355 nanometers. Okay, now we can analyze the data. I'm not going to go into that. We can determine the spatial position of each individual atoms and their chemical identities. And we can do that with sub-nanometer scale resolution, i.e. on the angstrom scale. And this is why we can do it. You see here, we get the coordinates of the atoms, X, Y, and Z, and that gives us the three-dimensional reconstruction. We get the times of flight from a very simple equation, and that's potential energy equals kinetic energy, where N is the charge state, E is the charge on an electron, V sub 0 is the voltage that you apply to the tip, M is the mass of the atom, and D is the flight path, and T is the time of flight. So you see you get something like mass to charge state ratio is equal to a constant, 2E, the voltage, or when we pulse with a laser light, we have a voltage plus an effective voltage due to the laser, and then the time of flight, which we measure, and D is the flight path. And how do we get D? So we take a specimen like tungsten, and we know what the isotopes of tungsten are, and we know hence where they should be in a mass spectrum. And then also at the bottom end of the periodic table, we have hydrogen, and there's always some hydrogen, a little bit of hydrogen in the system, and we know what its mass is. So we have two data points. Let's say tungsten 186 and hydrogen, and it turns out it's completely linear. So we can interpolate to get the masses of other species. Okay, what is the atomic resolution? The interplanar spacing, that's less than 1/10 of a nanometer. The lateral resolution within the plane is 0.3 to 0.5 nanometers. And HKL is just a crystallographer's way of identifying different atomic planes. Okay. So I'm going to show you now how we would analyze wafer-based materials. And we can analyze materials in 1 hour. We can get a lot of data using the laser light. And we've had data sets, I will tell you, a billion atoms now. So we can access a lot of material then. A billion atoms is a lot of material to us, but also to the integrated circuit technology, a billion atoms is a lot of atoms. And you see here is your tip down at the bottom. Here's your tip. And it's the distance from the tip to this cone-shaped with an orifice is about 10 to 50 microns. And then the flight path, as I've said, is between 80 and 120 millimeters. And over here, the detector that we detect everything with is about 80 millimeters. So this is the essence of the local electrode atom probe. So I'm looking at some this is performance comparison. Let's say first generation atom probe, the analysis time was 2 to 6 days. The field of view was 20 nanometers, and the specimen type was 5 millimeter needles. And now with the LEAP, we can analyze in 10 to 60 minutes, let's say 60 minutes, we get a reasonable amount of data. The field of view is about 200 nanometers. That is
It's
200
11 hours.
by 200 nanometers. And we use microtips and needles. And there are sophisticated ways now of making those very sharp. Okay, typical mass resolution was about this is the full width at half maximum for the typical mass resolution, about 1 part in 500, and the same is true now with the LEAP. This is an early example, but it'll give you an idea. This is a conventional tomograph, and this is the analysis direction going from left to right. The cross section here is rather small, 16 by 16 nanometers, and the length of this is 60 nanometers. And what you see are precipitates here. These are precipitates, and the volume of this is about 16 by 16 by 195 cubic nanometers. And this is very early on. This is from one of our very first data sets. We could detect about 2 million atoms in 1.5 days. And now we can detect 1 billion atoms in about 6 hours. And there are 23 precipitates in this alloy. It's a nickel aluminum chromium alloy. Okay, now with the LEAP tomograph, this is still early. The volume's about 90 by 90 by 60 cubic nanometers, and we detected 10 million atoms in an hour. So that's 90 precipitates, and that's a lot of data. At that, even though this is small by what we can do today, this data set, it contains a lot of information. Now we can extend all of this with laser pulsing. And over here you see a microtip post. This is the microtip post. And we cut out a piece of material which has this shape here. And then we can glue it. We can glue it with platinum as a weld to this silicon micropost. And here is my tip over here. And you can see in this region here, if I blow it up, it has layers of different material which are indicated by different colors. And so we can look at thin film multi-layers, which are quite common in the semiconductor industry. We can, of course, look at semiconductors. We can look at glasses. We can look at ceramics. And we also now have been looking at nanodiamonds. So here is a picture now of it, just to make sure all of this is clear. And this is one of our early results. Here we have an array of silicon nanowires. They were grown by a technique, it's called vapor liquid solid, and gold is the catalyst, and hence the yellow gold. And so we have an array of these, and here is my local electrode, and here is my position sensitive time of flight detector. And this is also an early result. You can see the date on here, 2006. And you
David, just a question, David. Is the local electrode used to accelerate the particles that are being emitted, or what is its role?
Okay, you can see over here. That's a good question. You can see over here this whole thing with these silicon nanowires on it is at Earth potential, and we can apply a potential to the local electrode.
Right.
And when we apply a potential to the local electrode, then you evaporate the atoms. But this is in a pulse mode.
Got it.
And these are electrical pulses.
Yeah.
When we use a laser, we shine the laser beam directly on the tip. And actually, in practice, we use a combination of voltage pulsing plus laser pulsing.
Thank you. Got it.
And here you see what you see. This is the screen over here. This is a screen, and it corresponds to the position of a detected atom. This is an XY spectrum. This is just in 2 dimensions, but each spot here corresponds to one detected atom. Okay, over here, this is an artist's conception. You see, you're hitting the tip with the laser light, and the atoms go through this orifice in the local electrode. And this is a schematic of what the electric field above the tip looks like. When you use laser pulses, first you're applying, this is potential energy here versus distance. And this is my tip with all the atoms. And this is at a positive potential with respect to Earth. And what that applied field does, if this is potential energy of an atom, over here, this is dark green and then light green. This is without the applied voltage. With the applied voltage, you introduce this hump over here. It's given a name in the field. It's called a Schottky hump after a well-known physicist. And then you apply the laser light, and it excites that atom. It excites that atom that goes over that Schottky hump. And once it goes over that Schottky hump, it becomes positively charged. The tip is positively charged. So it goes along the electric field lines indicated by these arrows. So the atom would come from this point over here, say, or this point over here. And this is an electric field line. It goes along the electric field lines to the detector. We use something that actually we developed at Northwestern, a so-called proximity histogram, because the information is in 3 dimensions, but it's cumbersome to analyze it in 3 dimensions. So we invented this technique where we have a nonlinear composition profile, compositional surface. It's an isoconcentration surface. In other words, constant concentration surface, say around a precipitate. And then we can convert that into 2 dimensions. I won't go into the details, but say you have 2 atomic species, yellow and orange, and this is your interface position, which is a definition, and you can see you then wind up with a concentration profile of yellow atoms and orange atoms, or say nickel atoms and aluminum atoms, silicon atoms, and phosphorus atoms. So it's a way of getting 2-dimensional information from a 3-dimensional object. I'm going to skip the details of how we do that, but I'm going to skip all of it. This was work done on indium arsenide nanowires, and here is a gallium arsenide substrate, and you can grow on that gallium arsenide substrate. You can grow what are called nanowires, and these are the nanowires here. And this is a scanning electron microscope image of those nanowires. The top half is just an artist's conception of what those nanowires look like. And here is a single nanowire. Here's a single nanowire. And this is an SEM picture, scanning electron microscope thing. And it doesn't have very good resolution, you can see, because you can't see the detail that I'm going to show you. Okay, now here is the same material, indium arsenide, and the arsenic atoms are greenish and the indium atoms are kind of purple. And this is this is really a three-dimensional object, but what you're looking at is a two-dimensional cut through that three-dimensional object. And every spot corresponds to a single atom. And you can see the dimensions here. It's not all that clear. This is about 20 nanometers this way, and this is about 20 nanometers this way. But it's a nanowire, so to speak. And here's an SEM picture, and you see the wire is actually faceted, and it's hexagonal shaped wire, it turns out, and because those are facets that you're looking at, and you see these hexagons. And now here's a side view of this. Here's a side view of this nanowire, and this is about 300. This is about 300 nanometers long, and the cross section's about 22 nanometers by 22 nanometers. And here is the mass spectrum. Here is the mass spectrum. So on the left-hand side here, these are number of counts on the ordinate scale. And over here on the abscissa is mass. This is really mass to charge state. It's mass divided by the charge state. So for example, here you see arsenic, and down here there's a tiny peak of triply charged arsenic. And over here is doubly charged indium. Over here is singly charged arsenic, singly charged indium. And over here is an arsenic molecule, but it's singly charged. And over here there's a tiny peak of that same of a arsenic molecule, but it's 3 arsenic atoms, and it's singly charged. And how do you get concentration from this? If you know how to count, you can get concentration. So if you count the number of atoms under this peak, then you get the number of arsenic atoms. And you do the same thing for this peak. You count the number of atoms, and then this tiny peak, you also get a certain number of atoms. Also have additional arsenic atoms, and over here you have additional arsenic atoms, and then that takes care of arsenic, and then indium atoms are here, and indium atoms are here. So by counting the number of atoms, you can convert to concentrations. So the analysis in that case is simple. And now here is the same specimen. Once again, you have 2 types of atoms, indium and arsenic atoms. And I just want to emphasize that each spot that you're seeing is genuinely a single atom. So it has single atom sensitivity. And now over here, you have indium arsenide that's been doped with gold atoms. And the gold atoms are, of course, yellow. There's lots of yellow atoms here, a lot of yellow atoms. And so if you count the number of indium atoms, the number of arsenic atoms, and the number of gold atoms in this volume of material, you can get the concentration of gold, and you can get the concentration of indium and arsenic just by counting. You don't necessarily do the counting by hand, of course. You see, in this case, there's a catalyst to grow this wire, and this is the catalyst over here, up here. This is the catalyst, and if the catalyst is gold, then you also see some gold atoms in the indium arsenic. I made that point before, there were gold atoms intermingled. So this is mainly gold, but what you see happening is that some of the arsenic atoms during this processing diffuse into the catalyst, as well as some of the indium atoms. So this is why this catalyst is not 100% gold, because you have some interdiffusion between the 2 species. So you're looking at interdiffusion on an atomic scale. And now the other thing that you can do, it's all done with software. And we build our own high-end workstations. Um, and and each of these is a cross section. So you can take cross sections and you then from the cross sections you can generate concentration profiles. And you can see what's happening as you go from the catalyst material, which is gold, into the indium arsenide nanowire. There are fewer and fewer gold atoms because you have a concentration gradient of gold. So you're seeing concentration gradients on a nanometer scale. And you see the date of this paper is 2006. It was one of our very first results. And I'm showing it because there's been a big evolution since we since we first did these kind of experiments. But what happens, our data sets keep getting bigger and bigger because we can pulse faster and faster, and we can collect faster and faster data sets. And I mentioned we can collect in 6 hours now from an aluminum alloy 1 billion atoms with thousands of precipitates. So the progress has been enormous in the field itself. And here are the concentration profiles. They're sitting over your. Here is the gold way up here, and then there is some arsenic and some indium in the gold. And then when you go to the right, you mainly have indium and arsenic, and then there's still some gold down here, but it's at a lower concentration. And so you get these atomic concentration profiles. Where am I at with respect to time, Ron?
Oh, I think maybe 15 minutes more. It's about 11:16. So I think
Okay,
another
so
10 or 15 minutes, and then we have some quick Q&A.
okay, so this involves the formation of silicides, which is important for the semiconductor industry, of course. And I did this with some research that was supported by the Semiconductor Research Corporation, the SRC. And it involved my graduate students and a colleague, Lincoln Lahone, and myself. Okay, so let me proceed with this. Okay, why are metal silicides important? So here is a transistor. This is a P-type silicon substrate. This is the source, and this is the drain, and this is the channel between the source and the drain. You see here is silicon dioxide on either side, and this is called polysilicon, and it's a metal silicide. It's actually a metal silicide that they use, and you can see above it here that they put a metal layer, and then this generates then, due to processing, a metal silicide. And what we wanted to know was, can we quantitatively say something about this metal silicide? It's a single transistor, and you can put a single transistor now in in one of these nanotips that you have. Okay. So titanium, for example, titanium disilicide, it's unable to form this for line widths of, say, less than turns out less than 250 nanometers, a titanium silicide. The cobalt silicide, its resistivity rises in very narrow lines. By narrow, and this is not narrow by today's standards, sub 100 nanometers. And this incorporates some junction leakage due to a rough interface at the metal silicide silicon interface. See, the channel here is pure silicon. Whereas nickel silicide, which is what we're aiming for, it turns out, nickel silicide is very good. It has a lower formation temperature, which is good. It has a reduced silicon consumption because cobalt disilicide is greater than nickel. It incorporates more silicon, obviously, than nickel silicide, but it has a poor thermal stability. It also, so that's the downside, is that its thermal stability is not great. So what's done is to add some palladium to improve the thermal stability of the nickel silicide, with the industry now replacing a palladium with platinum, which is expensive, but they make it up to the customer pays for that. Okay, so the film deposition, preparation of metal silicides, involves nickel palladium, say, 1, 5, or 10%, and it's deposited on a boron-doped silicon. It's P-type silicon wafer, and that's done with radio frequency magnetron sputtering. The processing is between 400 and 800 degrees C for 30 seconds, or furnace annealing in a nitrogen ambient 550, 600, or 650 degrees C. All of these numbers now are out of date because, it's just become more and more sophisticated, the whole semiconductor industry. So how do you make 3D leap tomograph samples? Well, what's done is what's called rapid thermal processing, and it's done at 600 degrees C for 30 seconds, which is a typical process in the semiconductor industry in the era that we studied these materials. And then you post anneal at 650 degrees C for 30 minutes. So the estimated thermal, the estimated thermal mass for all the post RTP processes. Okay, and then you use something that we call a lift-out technique, and we cut with a dual beam fib, a focused ion beam machine, which is quite expensive, and we can cut out material. And you see here a microprobe is attached to the material. And the cross-section of the material we cut out is triangular shaped. It has a triangular shape. And then we put these on a coupon that has microtips. We add them to this coupon, so we create many specimens from this one specimen. We salami slice this. We salami slice this piece of triangular shaped material, and this results in a lot of microtips to analyze, which is important because you want to get good statistics. So you want to look at a lot of microtips. Okay, so here is the microtip post. Here is the silicon wedge, and then it's cut off. You see, it's cut here, and we weld it on to this microtip, usually with platinum. I think I showed you this already, and you can see the cross, and you can see this bit of material here. That's my specimen. This is my specimen here, and I cut it off and attach it to this microtip post. And then there are two welds here. There's a weld here. This is a platinum weld. This is my microtip here. And this part over here is the region of interest. And that's what we're going to analyze with the atom probe. And actually in the semiconductor industry now, one of my students, a former, not student, but a research associate, Sung-Il Beck, he works for Intel in Portland, Oregon. They have a facility, and he uses an atom probe as well as transmission microscopy to analyze circuits for them. And here's the local electrode that you can see. and you bring the local electrode up to each one of these specimens one at a time to analyze them. Okay, so now what's done is to measure sheet resistance, which is ohms per square. So if you look at just nickel palladium with 1% palladium, it looks something like this curve here. And this is the room temperature. This is the rapid thermal pulse temperature. And you can see over here in red, nickel palladium, 5%. And you can see the number of ohms per square decreases with the increasing concentration of palladium. Well, this is more data of the same type on the right-hand side. Okay, so we could say, make a verb out of it. RTP'd at 600 degrees C for 30 seconds. And you can see the silicon is blue, the palladium is red, and the nickel is in green. The nickel is a coating. We don't necessarily use nickel, but we want to put a coating on the material so we can analyze it. And you can see here that you're able to look at the distribution of palladium. This is number of counts in this direction. No, I'm sorry. This is the dimension, not number of counts. This is the dimensions, and the dimension here, the width goes from -15 to +15. So that's 30 nanometers. And then in depth here, this is about 40, 50 nanometers or so. And now you can look at it's not composition, the word should be concentration as a function of distance along it. And you see in green is the nickel, and then the silicon is in blue, and the palladium is in red. So you have the two most important elements here are the silicon and the palladium. So you can see the distribution of those two elements very nicely. And all of that is relevant to the semiconductor industry. Okay, then here's another example where the data is better. This is concentration of nickel and silicon. The silicon, once again, is in black. The palladium is in red, and the nickel is in green. And you can see the nickel silicide is very close to having a 1-to-1 ratio. So this is really nickel silicide. And then down here is the distribution of the palladium in the nickel silicide. And all of this is what the semiconductor industry is interested in. And they're also interested in how the specimen, of course, the end product, how it compares. Let me reword it. They use a certain processing technique, okay? And then they get a certain result, and they're looking for an optimum result. In this case, they want nickel silicide with palladium distributed uniformly throughout the nickel silicide. And here's an even nicer example of this. You can see here concentration versus thickness. And you can see that the silicide is almost stoichiometric, not exactly stoichiometric. Here is the palladium distribution. And what's new in this is that what you have at the end, and to the right here is silicon. The black is silicon. And what you see is that you have segregation at that interface of the palladium. So that's interfacial segregation. And using classical techniques, there's no way of knowing that you're getting interfacial segregation. And you can see the scale of things here. This is 0 here. That's the interface. And you see the width here is quite small. It's maybe about 1.5 to 2 nanometers thick, that interfacial segregation. And And to put it in more quantitative terms, it's about 3.4 extra atoms per square nanometer at this interface over here. And that gives you an idea of the sensitivity of this technique to very small coverages of the interface. And you can also get out chemical roughness of the interface. This interface has a root mean squared roughness of about 0.78, 0.8 nanometers, let's say. See, this is the green, this is the green, this is the silicide, and this is the roughness of the interface, which says something about the resistivity also of the interface. And here's a beautiful example, actually. You can see the stoichiometry over here is about 1-to-1. And the palladium is sitting substitutionally then on the nickel sites over here. And then once again, at the interface, you get a different kind of behavior from the bulk in quotation marks. Oh, we did some calculations on this. I'm so our feeling was from the experimental data that palladium is sitting substitutionally on nickel sites.
It's 11:30.
So you can see here, it's nickel 1 minus X, palladium X, silicon is more stable than nickel silicon 1 minus Y, Y. And so we looked at pure nickel silicide, and then we looked at this one where X, palladium is X, so this is nickel is 1 minus X, and we looked at it here where it's Y, and this is palladium is Y, and we could say which one had the lowest energy. It's this one here, minus 455. So 45, 100, minus 145 EV. So this has the lowest energy. This is higher energy. This is higher energy. And this is the, I'm sorry, this is. So this silicide here is more stable than this silicide. So the conclusion from all of this, and this is a scientific answer, is that palladium is sitting substitutionally on nickel sites. And this is a summary of what I just told you. So I'm going to stop here. I'm going to stop here and give credit where credit is due. The NSF and O&R for funds for the LEAP tomograph, O&R for the picosecond laser upgrade, and then the people at, these are all the people at the company that was called Imago Scientific, and now it's called Kamika. And then Dr. Zhugang Mao, he did some first principles calculations for us at Northwestern. And Dieter Isheim, he manages a new cap. He's worked with me for 25 years. Okay. So I know him very well. I think that brings me right to half past.
Very good. Very good. David, thank you very, very much. For those who may have tuned in after we began, I just want to say we had a problem with the PowerPoint presentation that David had intended to use today. But honestly, David, in retrospect, what you talked about is actually as relevant as to our interest as anything might have been. So maybe the gods were watching and decided we should hear more about microchip fabs and so on. Because we had a conversation a few weeks ago with Jesus Del Alamo from MIT, and he talked about nano features on semiconductor microchips that are evolving in the technology right now. So this is all very relevant, and I want to thank you, David, for adjusting on the spot, given that this is a totally different PowerPoint presentation than you'd intended. But you just handled it beautifully, so I thank you for that.
Okay, so you're welcome. I wanted to say, in terms of the semiconductor industry, all of these numbers are probably outmoded.
Yeah.
the lines get finer and finer and finer in the
Oh,
semiconductor.
absolutely.
And
No,
it's
but I wanted to follow up on that. You mentioned that you have one of your students is at Intel and using some of these technologies.
right.
I'm just curious, do you have continuing interaction with the semiconductor fabs and manufacturers?
Do I have, you know,
Do you continue to interact at all with the semiconductor folks?
only through the SRC, the Semiconductor Research Corporation.
Yeah.
Um, Intel is highly secretive. You cannot get information out of them. I once,
Yeah.
I once wanted to get some gallium. They were working on gallium arsenide, Intel, and I was at an SRC meeting, and I spoke with the guy, and he was at an Intel facility, a different one than the Portland, Oregon, and he said, "Oh,
Yeah.
I'll get you specimens." And then it never materialized because I guess he checked with his managers, and the managers didn't want him to give me the specimens. So they're highly secretive because it's a very competitive industry,
Yes.
and knowledge is king. And they just didn't want me to know what they were doing.
Let's see.
I could have,
I see a hand up. So Vincent, do you have a question?
Yes, I was actually curious because the word annealing was mentioned, and I only partly understand how it strengthens a metal. But many years ago, when there was actually a real world application, the John Harvard statue had some vandalism, and when they went to clean it, they decided to anneal the metal of the John Harvard statue. And I was wondering if what annealing was doing in strengthening a piece of metal that was on a statue and how technologically that works. Talk about real world.
well, so annealing is a word that's used by different people to mean different things. In the case of is when you anneal a specimen or age a specimen, you can produce precipitates, and those precipitates harden the material. And a really important example of that are alloys that are used, nickel-based superalloys that are used to make turbine blades that are used in jet engine and military alike. They produce a second phase which occupies something like 80% of the volume of the material. And because of that high volume fraction, it's very hard for dislocations to move, and dislocations, they produce plasticity. So, and if dislocations have a hard time moving, the material is strengthened. Um, and those commercial alloys, they contain up to 10, 12 elements, and each element has a different job to do for the alloy. And people have been constantly improving these nickel-based superalloys, and it's really on a plateau. They operate maybe at about 1100 degrees C, these turbine blades, but the increment of the strength that you get per year is very small. So I've been working for almost 10 years now on cobalt-based alloys with the objective of supplanting nickel-based superalloys um, for turbine blades. And we're not there yet. Alloy development, it's not for the faint of heart.
Yeah.
It's
Just to add another comment, David, on the question of annealing. Vincent, if you look at welded structures, you often find that welding, because of the thermal stress that is produced during welding operations and the expansion and contraction that occurs in a welding operation, welds are often left in a state of mechanical stress. And so it's not uncommon to anneal them, to heat the welded structures after they've been processed or produced to relieve the stresses in the welded area. And that's another form of annealing. If the stresses are not relieved, it's possible that the welded structure could go into service And given the local stress, it could crack prematurely. So it's not uncommon for post weld heat treatment or annealing to be a common metallurgical practice in many metallurgical structures.
Well, that does answer at least part of my question because they said that once the statue was cleaned and annealed, it would look better and withstand the outdoor weather that it's subjected to. And John Harvard never looked better. But it was interesting that a metallurgical process was being applied to a statue that was in the outdoors.
Yeah.
And it does have a fresher, cleaner, and more durable look than it had when I was growing up. So there's a real world application of some sophisticated technology.
David, I said just mention for your benefit here, Vincent Dixon is the forum's resident historian, so he knows about people like George Washington and other folks whose statues adorn our landscape. So thank
Uh,
you, Vincent, for that question.
yes,
Thank
thank
you.
you. And thank you also, Ron, for filling in some details about stress relieving.
Right, right. Let's go to Michael.
I've switched to my computer, so can you hear me?
Yes.
Okay, great. So one thing that was surprising to me is when you're looking at the compounds that you were visually, they weren't well ordered, as in a checkerboard, for instance, and they seem to be randomly located, the atoms in relationship to each other. I was wondering whether that has an impact on the characteristics of the compound. Uh, uh, um, and the second thing I would wonder is that on a quantum level, we know that electrons act differently as particles versus waveforms, depending on whether through the double slit experiment they're being observed or not. And I'm wondering whether that characteristic of electrons has any impact on your level, which is not quantum, subatomic, but atomic, if I'm asking the question clearly enough.
Good.
I'm not sure I follow you 100%, but the part about randomness, yes, most of these alloys that we looked like are not ordered alloys. We have looked at ordered alloys, nickel-3 aluminum, and we can see it's not like in a perfect lattice made out of ping pong balls or ball bearings, but we can see the ordered planes and we can distinguish the degree of order in the planes. And this business about randomness is quite important with respect to the nucleation of a new phase. And it's something that's still, the nucleation of a new phase is still a problem from an experimental point of view that hasn't been solved yet, really. Mathematically, you can work out nucleation theory and predict the critical nucleus size and all of those good things that you learn in school. But then when you come to the practical side and look at a real alloy, the whole question of nucleation of the second phase is still, I would say, problem to be solved in detail.
Wow, very interesting. On the other part, maybe I didn't say it that clearly, but the double slit experiment shows that when an electron is passing through a double slit and it's being observed or they're being observed, they act as particles, whereas when they're not being observed, they act as waveforms.
Right, yes, yeah. That's a classic.
Does that have an impact on your work?
No, I don't think so.
Okay.
Interesting point. Thank Michael.
You're welcome.
Yeah, I have a question or a comment. When I was at the lab, I worked with the fab. They had a microelectronics laboratory, and they manufactured CCDs for many of our projects. And we always ran into problems, at the fab with, issues related to, contamination and the like. So could you actually, with your device, I couldn't quite get the the scaling rate. But could you actually, analyze an individual CCD1 detector and look at, sort of the spatial profiles of dopants in a like a CCD?
Yeah, we could in principle do it. We've never done it. It would be an interesting problem to tackle, to look at CCDs. Yeah.
Yeah, because we particularly had, again, issues with issues with improper doping or in some cases even contamination, and so trying to look at the structures. So this would in fact in theory work for that. That's
Yeah.
correct. Okay, yeah, it's a really interesting capability to look
Yeah.
at the atomic structure level of materials.
Yeah, the interesting part of what you say is what you said is valid in that people bring us problems. Like what I wanted to talk about were these nanodiamonds that are found in meteorites. Well, I shouldn't say meteorites plural. In the Allende meteorite, they came to me with this problem and they said, okay, we know what the ratio of of of, uh, of the isotopes are in of terrestrial material, but we're interested in pre-terrestrial material before our, our our solar system was created. What's the ratio? Well, so and that's how we got started with that problem. I was unaware of the problem, but people brought it to us.
Yeah. I have a question about David, about the work you presented on indium arsenide. Um, I, I was the semiconductor. When you looked at the elemental distribution, you actually found that the arsenic was present in three different oxidation states.
Yes,
Did that surprise you? I guess I
that's an
wouldn't have
excellent
expected that.
that's an excellent question. When this whole field of atom probe tomography started, people
Yeah.
thought everything should come off in the singly charged state.
Yes.
But it turns out it's not true, that it can come off in different charge states, but the ratio of the charge states is something that there's not a good model for at this point. But we know from a practical point of view that the charge states are not singly charged, and they're not doubly charged 100%, but there could be an admixture of the two.
Does that affect performance in any way? Or is it important in terms of the semiconductor performance that there are different oxidation states?
No, that's the technique.
That's a feature. It's an artifact of the technique, not is
Yeah,
that correct?
no, it does not affect the performance.
Okay.
No.
Okay.
For example, we see arsenic, we see dimers and we see trimers.
Yeah.
It's an artifact of the technique. It's not
Yeah.
intrinsic to
I get it. I get
the
it.
material.
Yeah. The other thing that interests me was the detection of interfacial segregation that you pointed out near the end in your discussion. That turns out to be extremely important in a whole array of materials degradation phenomena. For example, the presence of metalloid elements like sulfur or antimony or molybdenum at the interface, at the grain boundaries in metallic materials, high strength metallic materials, can lead to embrittlement.
Right. No,
And so that becomes really important. Is that something you're still working on, or have
oh yeah,
you?
yeah. That you hit the nail on the head, so to speak. We're worried about cohesive energy, and some of the materials we've made, say the cobalt alloys, they're extremely
Yes.
brittle. And we discovered that because a graduate student dropped a specimen on the floor and it shattered into small pieces. So to overcome that, we added boron and zirconium. The boron and zirconium segregate to the interface, increase the cohesive energy,
Right.
and hence the material is no longer brittle.
Well, that's interesting because I've done some work on materials of construction for hypersonic vehicles, which are likely to use hydrogen as a fuel. And there's a great deal of concern. If we actually build a space force, well, we are building a space force, but at some point we're going to have to build vehicles that are hypersonic, and the materials of construction is still, in many respects, an open question. And when you consider hydrogen as a fuel, you've got to consider the fact that hydrogen embrittles, particularly the high strength material. So it's a perversity of nature that you want to build these vehicles out of high strength materials, but the materials are sensitive to the fuel you're going to use. So it's a little bit of a dilemma.
That's 100% right. We're actually studying in a steel. We're studying in a specific steel. We're studying hydrogen segregation at defects. And one of the defects in a steel, so to speak, is carbon. And
Yeah.
we do this by deuterating the specimen. We use deuterium because there's a lot of arguments about hydrogen.
Yeah.
What's the origin of the hydrogen, whether it's intrinsic or extrinsic. So we use deuterium, and you can then see there's a one-to-one correlation where the deuterium atoms sit and where the carbon atoms sit.
Yeah.
I could have brought a slide. I could have brought a slide on that, but I didn't.
Okay. Well, David, I want to thank you for joining us today. And I appreciate that, number one, you had to adjust your schedule in order to accommodate the timing of the seminar, the forum today. And then secondly, I just want to tell you how masterful your job of accommodating the problem with the PowerPoint. For some reason, we could not open the PowerPoint you wanted to use today, and yet you gave us a brilliant presentation on atom probe tomography. So I want to thank you for that, David.
Thank
Um,
you. It
and
was
on behalf of all, I told you that we'd finish before 4:12. I know you have to travel today, so I want to bring the meeting to an end, but I want to thank you on behalf of all of us for joining us today. Thank
okay.
you very much, Dave.
Thank
Take
you for
care.
being a fantastic host. Okay.
Take care. Take care, everyone.